Okay, in this talk, I'll be presenting our work on the streaming complexity of SVMs. This is joint work with Alexander Andoni, Yi Li, Sekire Mahabadi, and David Woodruff. Okay, so the outline of this talk is I will first go over some background on SVMs and what the problem we focus on is. Then I'll be giving an overview of our main results without too many details of the actual techniques we use. But then I'll give a proof sketch of one of these results, namely the optimization that we're bound. Okay, so what are SVMs? Well, this is a very classic algorithm in machine learning, and it's received quite a bit of attention in theory and in practice over the past decade or two. On the other hand, there's been extremely little work on SVMs in the streaming setting, which is what we consider here. So here we view the number of data points n as being very large, and they come to us as a stream instead of all at once, and we want to use as little space as possible. Okay, and so the basic idea of SVMs is you want to find a good linear classifier, and in particular, the objective that the SVM algorithm minimizes is the following. So basically, it's this function f that has two terms. So the first term is this, you can think of it as a regularization term that tries to make these parameters as small as possible. And the second term is basically saying if a given data point, xi, yi, is misclassified, then penalize it. If it is classified but not classified very well, then penalize it a little bit. And if it's classified and classified quite well, then don't penalize it at all. Okay, so this is the hinge loss, and this is the SVM objective. Now this is a slight modification of the standard version. This is bias regularized, meaning that in this first regularization term, we have the bias B included. And basically this makes it easier to analyze theoretically, and it also makes it strongly convex, so it actually makes it easier to optimize. Okay, so what is the problem we focus on? We focus on the streaming setting. So we have a stream of n data points, and we have two goals. So the first goal is what we call point estimation. So at the end of the stream, we want to be able to give the following guarantee. So given any theta b, we want to approximately output the value of the function corresponding to these n data points that were in the stream. We want to output this function for these given parameters. Okay, the second goal we focus on is optimization. So at the end of the stream, we want to be able to find parameters that approximately minimize this objective. Okay, and in both cases, we want to minimize the space usage, and we want to do so without any distributional assumptions on the data stream. Okay, and there are a couple naive approaches that work somewhat well as baselines. And I guess just as a quick note before doing that, getting into that, for most of this talk, I'll be letting lambda be a constant, so mostly ignoring that. Of course, in the paper, we do deal with that more precisely, but for the most part, you can just think of it as a constant. Okay, and so again, the first problem is point estimation. So we want to estimate the value of the function using these data points that were in the stream. And so one way you can do this is just by sampling, during the course of the stream, sampling something like 1/epsilon² points, and then using these basically as an estimate of the value of the function. And this immediately, it's very easy to show, this immediately gives you an additive plus minus epsilon approximation for point estimation. Okay, and for the second problem of optimization, you can do something quite similar, which is simple, in this case, 1/epsilon points instead of 1/epsilon². If you sample 1/epsilon points, and then in this case, you run SGD, stochastic gradient descent, on these points, as though you were optimizing the objective just using these this subsample, then this, again, gives you an additive plus minus epsilon. In this case, that means that the function value of the parameters found this way is within epsilon of the optimal value of the function for the optimal parameters. Okay, and so for each of these, the space usage is d/epsilon² and d/epsilon respectively. Okay, so you should think of these as the baselines that we're trying to beat. Okay, and so I guess one perhaps natural question is, before even starting with an additive approximation, why can we do even better? Can we get a multiplicative approximation? And so we show that when d equals 1, you can actually do this for point estimation. In particular, we show an algorithm that achieves a 1 plus epsilon factor multiplicative approximation with roughly 1 over epsilon squared space. So the same space as before, but this time we get 1 plus epsilon multiplicative instead of plus minus epsilon additive approximation. Okay, and again, I don't have time to go into detail for all of these results, but of course the details are in the paper. At the same time, we show that for d greater than 1, we can't hope for multiplicative approximation. In particular, for d equals 1, d greater than 1, such an approximation requires linear space in n, which is exactly what we're trying to avoid. Okay, and so this is what motivates for the rest of the paper. We focus on an additive approximation. Okay, so we show that you can do much better when you do allow an additive approximation. In particular, when d equals 1, we can get a 1 over root epsilon space upper bound. Okay, and this is much better than 1 over epsilon squared, which is what you'd get from this naive sampling algorithm. Okay, and similarly for d equals 2, you can get epsilon to the minus 4/5, and you can extend this to get something better than 1 over epsilon squared for constant d in general. Okay, and we'll show later on that you can actually use these point estimation upper bounds to also get optimization upper bounds, but that'll come a bit later. Okay, and so we also complement this with lower bounds for point estimation. And so we have 2 of these again. So one for the low dimensional case. So you can show this lower bound of epsilon to the minus d plus 1 over d plus 3. Okay, so if you plug in d equals 1, this is epsilon to the minus 1/2. And so this is exactly, this matches the upper bound of 1 over root epsilon that we get with our upper bound. Okay, for d equals 2, it's not quite tight, but it's fairly close. So you get epsilon to the minus 3/5. Okay, and as d increases, this goes to 1 over epsilon. Okay, so it's not tight for large d. And so we also complement this with a different lower bound, specifically for large d. So by large, we mean these being something like polylog n. And since you can think of n as something like polynomial in 1 over epsilon, and so this is like log 1 over epsilon. And so we can show that for additive plus minus epsilon point estimation approximation, you need at least up to polylog factors d over epsilon squared space. And so this is, again, up to polylog factors. This is basically matching the naive upper bound that you get from sampling. Okay, so it turns out that for large d, for point estimation, sampling, that the naive algorithm is tight. That's what this is showing. Okay, so that was point estimation. But it turns out that you can relate this to maybe the problem that one might really care about, which is optimization, which is finding these parameters, theta b, that do a good job and that have low loss according to the subjective function. Okay, so in particular, given an upper bound for point estimation, you can turn it into an optimization upper bound by, well, I don't have time to go into detail, but basically using a standard net argument, you can take a point estimation algorithm with space S and turn it into an optimization algorithm with space SD. And so if D isn't so large, that's like logarithmic in 1 over epsilon or something, or a constant, then this gives us pretty much an S space optimization algorithm. And so remember that for constant d equals 1 and 2, we had a 1 over root epsilon and epsilon to the minus 4/5 upper bounds respectively for point estimation. So basically this is giving us upper bounds for optimization that are polynomially better than what we got from SGD, which was 1 over epsilon. Okay. So this is optimization upper bounds, but the final main result that we show is lower bound for optimization. And this is a bit trickier to reason about, but and I'll go into it in a bit of detail. But basically, you can show that optimization requires 1/root epsilon space. Now there are some additional assumptions here when d is constant. In particular, you start to need to be a bit more careful with lambda, this regularization parameter from the objective, which so far I've mostly been ignoring. But basically, you can also get this for constant d, at least d greater than or equal to 3. Okay, and with that, you get this pretty much without any assumptions when d is like log 1/epsilon, so when it's large. Okay, and the basic idea of this is you can encode bits using these data points, and then you can decode the data points knowing the optimal parameters. And then finally, you can approximate these optimal parameters knowing you can approximate the optimal parameters using the approximate parameters that you get from the sketch, from the optimization sketch. Okay, and so in particular, we will reduce from the indexing problem. And so again, like I said, we'll assume here that d is something like log 1/epsilon, but this can be relaxed with some slight additional assumptions. And so Alice will add n/2 points. It'll be clear why I'm saying n/2 a bit later. Alice will add n/2 points to the unit sphere by encoding the ith bit using the location of the ith point. Okay, and so just to remind you, the indexing problem is Alice encodes some bits, in this case using the sketch that we assume exists, and then she will give that sketch to Bob, and Bob will, given an arbitrary index I, Bob will be able to decode the ith bit with constant probability. Okay, and the guarantee of the indexing problem is that this requires space that is linear in n, and that will give us the guarantee that we want. Okay, and the difficulty here is really in reasoning about the influence of a single data point, since the only guarantee we have from this sketch is that the parameters that it outputs is an approximately good. It approximately minimizes the objective. This is sort of a property of the entire data set, not just a single point, and so sort of hard to isolate just the influence of a single point. And so that's really what the proof is all about. Okay, and so in particular, we'll just define basically n candidate locations on the unit sphere, so v1 through vn, and these will be basically such that the inner product between any pair of these is somewhat small, less than 0.9. Okay, and such a set of examples of locations exists when d is like log 1/epsilon, or logarithmic in n in this case. Okay, and so Alice is given this bit string b of length n/2, and she will encode these bits by doing the following. So if the ith bit is 0, then she will add a point to, you can call it vi, with label -1 to the data set. Okay, and this is again by basically adding this to as a stream element to the sketch. And then if bi is 1, this bit is 1, then basically puts this point at a different location. Okay, and so then the problem basically becomes, can Bob query, given this sketch, can Bob query whether there's a point in the data set at the location bi? Okay, and that's sufficient to decode whether the bit is 0 or 1. So how does Bob do this? Well, one of the properties of this sketch is Bob can always add more points. And so to query the location bi, again, we're assuming this is on the unit sphere, Bob can actually add n/2 additional points, and he can do the following. So he can add n/4 points just a little bit closer to the origin from vi, and a little bit past vi. Okay, and so think of this as 0.99 BI and 1.01 BI. And in this case, the labels are +1 in each case, unlike all the other points that Alice added, which have label -1. Okay, and that'll be relevant for some of the details. Okay, and so one of the key properties of this is that only these n/2 added points and possibly vi are support vectors. Okay, and support vectors are a point is a support vector if it, loosely speaking, if it contributes to the loss. Okay, and it turns out that the optimal parameters are completely determined by the support vectors in the data set. This is just a standard property of support vector machines, and it's one of the key properties that we exploit. Okay, and so like I said, these optimal parameters are completely a function of these added points, and if there is actually a point added at vi, this location, then it's also a function of that. But in either case, Bob can compute these optimal parameters exactly. Well, up to whether or not vi is there. Okay, and that's exactly what we want. This sort of allows us to isolate the influence of this single point, and allows Bob to sort of reason about which of these two cases is he in. Okay, and so just as some notation, let θ0 star and θ1 star be the optimal parameters when vi is not in the data set, when it's just these n/2 added points that are the support vectors, and for θ1 star when vi is in the data set. So you actually have n/2 + 1 support vectors. Okay, and one of the key claims here is that you can actually show exactly what these are, and the difference between them is somewhat large. So it's like 1/n. Okay, and this allows us to, if we can show that the approximate parameters θ hat that we find from the sketch, if that's sufficiently close to the true optimum parameter, then we can figure out which of these two cases we are in. Okay, so that's exactly what we'll do. So recall that the sketch is guaranteed to output some parameters θ hat, b hat, such that the value of this function is at most epsilon more than the value of the function at the optimal parameters. Okay, but also remember one other property of f, this function this objective function, namely it's strongly convex. Okay, and it turns out that one standard property of strong convexity is the following. So if we know that this first inequality holds, then we also have the second inequality, namely that the difference between θ hat and θ star, whatever θ star is, that's going to be at most something like 1/√epsilon. Again, I'm ignoring this lambda parameter, but you can put that in, of course. So, and what this means is when n is also 1/√epsilon, roughly, then if you work out the constants appropriately, then you can actually distinguish between whether a θ star is θ0 star or θ1 star. And this is exactly what we need to query whether or not there's a point at the location vi. And so this allows Bob to determine the bit vi with probability 0.9, let's say, and to decode the bit. And so this completes the reduction from indexing and shows that the sketch requires space linear in n, in this case linear in 1/√epsilon. So that's the end of the proof sketch. Of course, there are lots more details, but you can find those in the paper. So in summary, our results show that in low dimensions, you can do better than naive algorithms, these naive sampling algorithms. But it's not so clear in high dimensions. So you at least cannot do better in high dimensions for point estimation. As we showed, that's tight. But it's not completely clear with optimization. But it's possible that this 1/√epsilon lower bound could be tightened to 1/epsilon, which is what we get from SGD. And so here are a couple questions that open problems that remain. So one is we mostly focused on linear SVMs in this paper, but one common use of SVMs is in this kernelized setting, which loosely speaking means you can do all of this while implicitly working in some different feature space, so that ultimately the function that you learn is not actually linear, but it's just linear in some more expressive feature space, and this can give you a lot more power in learning the function that you care about. And so there are some ways that you could imagine trying to extend our results to that. For example, there's some work on like random Fourier features that allows you to solve kernelized SVMs using linear SVMs, but these also blow up the space, the dimensionality quite a bit, and so these aren't directly applicable. So this is an interesting open question. And another one is just closing these gaps between the upper and lower bounds that we show. And in particular, I think one of the most interesting questions here is stochastic gradient descent optimal in high dimensions or not? And I think this is partly interesting because it's such a general algorithm that this might suggest things for other problems in machine learning, other streaming algorithms and optimization problems. So that's all for this presentation. For more details, you can check out our paper, and thank you for watching.